So in my previous class, we talked about properties of rings as well as ideals, both left ideals, right ideals, and then few properties of integral domain and all. And then I talked about the group homomorphism, the ring homomorphism, and few properties of that. So we shall continue the same thing today. That means few more properties of homomorphisms, mostly group homomorphism. So in this class, I will basically emphasize on few of the properties that is very much related with the idea of generation. That means how an element can generate an ideal, or how few elements can generate an ideal, or how a non-empty subset can generate an ideal. So that's very interesting and important topic of ideal theory or the theory of rings. So we must study this because from many of the questions for competitive exams, many of the years we have seen that few questions are being asked from this particular part. So unless you have this concept of how an element generates an ideal, then it would be difficult for you to answer those questions. So in this class, we'll basically try to highlight those topics. But before that, let me start with the basic definition again of homomorphism. In my last class, I did few problems. So today also, we will go for few more properties of ring or group homomorphism. Okay. So as I mentioned, homomorphism is nothing but a mapping from say one ring to another. For ring homomorphism, say F satisfying few properties. For example, if this is R plus and dot, and if this is R dashed plus dashed and dot dashed, then ring homomorphism means it satisfies few properties like f of a plus b should be equal to f a plus dashed f b, and f of a dot b should satisfy fa dot dash fb, and that should satisfy for all ab belongs to r. Okay, if so, it basically preserves the operations plus and dot. That means even if you have this plus dash and dot dash, then also it should preserve this operation. So that's very important and very important aspects of ring theory. So few important terms like kernel of f. If we have homomorphism, then we should have a kernel of f. So what is kernel of f? All such element A belongs to R such that f of A must go to the zero element of R dashed. So that's the kernel. There is another important term that is known as image of f. So what is image of f? All such B dashed belongs to R dashed such that there exists some A belongs to R such that FA should be equal to B dashed. So that means all images. For example, if you have R here, so f of R. So you can understand that this image of f must be a subset of R dashed. So image of f should look like this. So this is image of f. So this is nothing but image of R under f. So many of the cases fr may be equal to fr. So this small f, small fr may be equal to r dash. Now please tell me in which case fr should be equal to r dash. What would be the extra property that we should impose over f so that fr equal to f r dash? Can anybody tell me when it will happen? When f is what extra
onto
property? When f is
onto
yes,
f must be
when
onto
f is onto as well as homomorphism, that means when f is an epimorphism. So when is epimorphism, then fr should be equal to r dash. So in general, image of f must be a subset of r dash, and you can see that some of the cases this image f may be equal to whole of r dash. So and that will happen only when this is an epimorphism. So that means homomorphism along with f is onto. So that's very important property. One thing we noted in our last class that kernel of F is an ideal of R. Okay, that we have already seen. The second question can be asked, is image F an ideal of R dash? What will be your answer? True or false? What will be your answer? Somebody? Is image F an ideal of R dash? True or false? Any answer from somebody? Is the question clear to you? Is image F an ideal of R dash? What would be your answer? True or false? Well, I am expecting answer from your side. What is your guess then? If not an answer, what is your guess?
So the image is an subring, but I'm checking the ideal.
Okay. So according to Aniket, he says that okay, image F is a subring of R dash. Okay. How to prove that? So for that we need to take two elements from let A dash B dash belongs to image F. Since it is in image F, that implies there exists AB belongs to R such that f of A equal to A dash, f of B equal to B dash. Then, so what you need to check? You need to check take an any element from R dash and then take a multiplication from left to check whether that's a left ideal or not. Okay, no, we want to check whether that is a subring or not. Okay, for that we don't need the property of ideals. So just need to check then A dash minus B dash. So that is equal to FA minus FB. But since this is an homomorphism, we have FA minus FB. Now see this, for this A dash minus B dash, there exists A minus B belongs to R whose image is A dash minus B dash. That implies A dash minus B dash belongs to image of F. But before that, we need to first show that image F is a non-empty subset. How to prove that image F is a non-empty subset of R dash? Because we know that F of 0 equal to 0 dash belongs to R dash. That implies 0, F of 0, sorry, yes. So 0 dash belongs to image of F. That implies image F not equal to empty. So many of the students I have seen that they just ignore this step, but this should be the first step. If you have any non-empty set, then only you can do all check all the properties of subring and all. So first thing that you should have that the thing that for example here we are checking whether this image F is non-empty or not. So first we need to show that image F is non-empty by some small simple argument. But I have seen many people, many students, they ignored this step. But formally writing, when you are going to write it formally, this should you should not miss this step. Okay, then what we need to show to check whether this is a subring, we need to show that to check A dash B dash belongs to image of F. Okay, again now A dash B dash equal to F of A, F of B. Since homomorphism, we have if that implies A dash B dash belongs to image of F. And that finally implies image of F is a subring of R dash. Now my question was little more. I am asking for whether image F is an ideal of R dash or not. Okay. Till now what we have checked that image F is a subring of R dash. Now
So
what
it is not an ideal.
is not an ideal? Okay. So somebody give me the answer that it should be false, right? So can you justify your argument? So he
Sir,
says that
we
yes,
sir we can construct an example.
yes, sure, please try.
Uh, just my I don't complete my construction. I just 1 minute.
Okay, just whatever you are thinking. See, it may be wrong. That doesn't matter.
I
So just
think I take Z and Z cross Z.
so he has taken Z and Z cross Z. Okay, then
Then I am constructing an homomorphism
okay, by how to define this? F of
f of n equal to n comma n.
okay, n comma n.
Um,
Whether this is a ring homomorphism. So
yes,
what? Yes, what to check is basically f of n1 plus n2. It should be f of n1 plus f of n2, and also you need to check f of n1 n2. It should be f of n1 into f of n2. So is this two properties are satisfied with
yes,
this?
sir. Yes, sir.
Okay, so this is a ring homomorphism. Good. Then
Then, sir, we know that in the ring Z plus dot, any subrings like NZ is a ideal. We if we take 2Z,
okay,
2Z is
so
a ideal of Z.
yes,
But
to z.
uh, but even 2Z homomorphic image of 2Z is not an ideal of Z cross Z.
Okay, you say that homomorphic image of 2z. What will this be? What will this be?
2n comma f of 2n comma 2n हो जाएगा.
So will that be this? Will that
It is
be
not ideal in Z cross Z.
so you are telling that this is not an ideal of z cross z. Why not?
Uh, mm, 2 comma 2 comma if we take 2 comma 1.
Okay, any element 2 comma 3 and take any element 2n comma 2m, then it becomes say 4n comma 6m, but still that is within 2z cross 2z, right?
Yes, I'm just constructing this example.
Okay, fine, it's a very good try, but at least uh, this is it an ideal? First of all, is what is your guess? Is an ideal? What will be your answer now?
I think it's not an ideal of Z cross Z.
Why not? So what will be your justification?
I'm thinking
Okay, yeah, please. But you had a very good try. Yeah, I mean, I want the students to come up. Whether that's correct or wrong, that will be checked. But you should come up and you should interact. That's very important because I have seen many students who are very good in maths, but sometimes when they go for some interview, they feel shy and they are not that prominent when usually they are. So I know them that they are prominent, but when they go for some interview, I have seen that they are not doing that well. So one of the reasons being they are not very much confident in speaking in English, or sometimes they feel shy when they talk with others. So in through this class, I will try my best to make all of you so that you should come up and give your answers spontaneously. It should not be like I should ask you the question and you may be wrong. That does not matter, but you should come up. Okay, so that's one of the special thing that I want in my class, that all the students should come up, and they should come up instantaneously, or on their own. It should not be like I should force them and then only they will talk. Okay, so anybody else? What is the, so you see that it's very innocent question that I asked you. Now you need to think a bit. Okay, tell me, is it true or false? Can you construct
Sir,
some example? Yes.
sir, I have an example.
Okay, to say it's false, right?
Yes, yes, sir.
Okay, okay, tell me.
So take the mapping from Z to Q,
If from Z to Q,
which map, which is the inclusion map.
if n equal to n,
Yes, sir.
for all n belongs to Z. Okay.
So now the image of Z contains the identity element 1.
Yes, image object contains,
Contains 1 and is a proper subset of Q.
is a proper subset of Q. Very good.
And this cannot be an ideal, but to
That
make it
implies,
explicit, multiply by half and see that
yes,
half times 1 does not belong to
that
Z.
implies image is not an ideal of Q. Okay, so again, you are giving another argument. That's a very good argument, and you have already mentioned that image of Z will certainly be Z, and uh, let half belongs to Q, and say 3 belongs to Z, then half into 3 does not belongs to Z. That implies image Z, which is equal to Z, is not an ideal of Z. Good. Okay, so both the arguments are fine. So yeah, that should be the way of thinking, that you should have many more arguments of a same problem. So the best that it should not be like once you are done is done. So try to find some other arguments as well, so that the same problem could be tackled through different angles. And if you think in that way, then what the best thing is that it will be helpful for you to remember other results. For competitive exams, this result might be helpful. Sometimes this result might be helpful. So if you have clear-cut idea what are the things behind it, then that would be easier. Now, so is it clear to all of you? Now you can see that this is not an ideal in general. Can you give me some extra condition that you can impose so that this could be, image F could be an ideal? Can you find some extra condition? Okay, so that's the homework. So in general, what is our conclusion? Conclusion is in general. So conclusion is in general, image F is not an ideal of R test. So in general, right? Uh, Now the question is, can you impose few more conditions on F so that, okay, so that image F becomes an ideal of R dash. Okay, so that's one of the extra condition that you need to think. So these questions are quite important because those questions that I am asking in throughout my classes, sometimes they are being asked in many of the competitive exams. So don't take it lightly. So if you see that I'm giving you these questions and not pursuing this question for my subsequent classes, that doesn't mean that they are not that important. So all the questions that I asked you are very important. So please take some time to solve those problems. So you have all those problems in your videos and all, and I will also share with you the whatever I am writing as an image. Okay, so up to this it's fine. Now I am just going very briefly about few important theorems, and that is known as first isomorphism theorem. First isomorphism theorem. I am sure that you all have done all those things at your undergraduate level. First isomorphism theorem. If you have not read this, you must go to any of the standard books and you should do it. And in these classes, I will assume basically you know first, second, and third isomorphism theorem. I will not emphasize much on second and third isomorphism theorem. They are important, but you should read it on your own. But here I will also mention the correspondence theorem that you might not have read this, or I will just explain it what does it mean actually, just the inner meaning of that. Okay, so first isomorphism theorem states that, so you for say this is for ring, the same thing happens for group as well. So it's for ring. It says that let f from R to R dashed be a ring homomorphism, then R quotient kernel of F. As I mentioned, when you have a homomorphism, you will also have the concept of card F. That must be isomorphic to image of F. So sometimes many of the authors they put some extra condition here. That is, they say that let F from R to R dashed be an epimorphism, that means homomorphism as well as onto morphism. And just now I have mentioned that if this is an epimorphism, then image F must be equal to R dashed. Then R quotient car F must be isomorphic to, in that case, image F will be replaced by R dashed because that's an epimorphism, means this is an onto mapping. As a result, this is R dashed. Okay, so I'm not going to the proof of this theorem, but for many competitive exam problems, this theorem plays an important role. So just for an example, what I'm saying that, okay, let us try to have an example here. For example, suppose Z2, I am defining a mapping from Fn by f of n goes to class of n. So you know what does it mean, class of n, for all n belongs to Z. Okay, let's see whether this is a ring homomorphism or not. For that, n1 say plus n2, n1 plus n2 equal to class of n1 plus n2, and this is of course equal to ff1 plus fn2. Similarly, f of n1 into n2, that is class n1 into n2, that is also fn1 into fn2. Okay, so this is true for all n1 n2 belongs to Z. So since these two properties are satisfied, we can say that this is a homomorphism, ring homomorphism. Now the question is F an epimorphism? What will be your answer? True or false? What is your answer? Somebody? Is F an epimorphism?
Yes, sir.
Okay, so the answer is true. So that you can very easily check, take any class, then for that you will certainly have the corresponding n here, so that f of n goes to this. So this is an epimorphism. So according to this result, by first isomorphism theorem, we have z quotient kernel of f must be isomorphic to Zn. Now the question is, what is kernel of f? What is kernel of f? So all such n belongs to Z whose image, that means f of n, should be the zero element of Zn. What is the zero element? Class 0. That means all such n belongs to Z such that f of n means class of n should be equal to class of 0. So what kind of n it should be? The n, oh okay, so I should not put n here, sorry. It should be x. I should replace it by something. Already I have used n, so I should not use a. I should use a here. Okay. So all such a such that a if a equal to 0. So all such a belongs to this such that a n equal to 0. And what should be this form of a? All multiple of n should be a class 0 in Zn. So all such this should be nz form. So as a result, what I will get from here, I will get the idea is then z quotient nz that should be isomorphic to Zn. And that's why many of the times we replace this type of things by simple Zn. That looks much better and in a compact way that we can write it. So it's a very interesting result. So with this first isomorphism theorem, we can prove that Z quotient nz is isomorphic. So this is a ring, this is again a ring. So both the rings, they have the similar algebraic structure. Now again I will go to another very interesting example, and for competitive exam this example plays an important role. Okay, so we have already seen the concepts of say Z and the polynomial ring Zx. That means all polynomials whose coefficient should come from Z. Now, if I want to define a mapping f to Z, then how it should look like? So a polynomial should look like this: a0 plus a1x plus a2x square plus say an x to the power n. Okay, and that should be mapped to some element. So you can see that there are plenty of choices, n plus 1 choices. So this 0, if you put it 0, then suddenly that will be a homomorphism. But what we need, we are actually trying to prove that this is isomorphic to Z. So the question is, what does this element or this ideal represent? So from the form you are very pretty sure that here this quotient is given and that is isomorphic to something, so that matches with the first isomorphism theorem statement. So maybe first isomorphism theorem may be helpful, and we will show that that is very much helpful in proving this result. So the question is then, this mod, this curl, or this is a tilde x, or this bracket x, that should be equal to kernel of f, right? So how we will define this so that that becomes kernel of f? But before that, this symbol you may not be aware of this symbol. So what does it mean? Okay, first I will go for that and then I will come to this problem once again. So what does this statement or this symbol looks like in terms of ring theory? So in terms of ring theory, this kind of symbols are very important, And every year many of the questions are being asked by using this kind of symbol. So we must pay some extra attention about this kind of things. Okay, so now let us switch from this topic to another topic, and then again I will come back to this particular problem. But before that, let me first try to explain this symbol. Okay, so we already had the idea of ideals and all. So now suppose R be a ring, R be a ring, let R be a ring, okay, let S a non-empty subset of R, okay. Now S must be, then we can see that S must be contained in some of the ideals of R, okay. So this ideal, for the time being I am considering left. The same thing will happen for right ideal, and if we consider for both sided ideal, then it is also true for both sided ideal. Now I made a statement, S must be contained in some of the left ideals of R. My question is the statement true or false? Somebody, is the statement true or false? S is any non-empty subset of R where R is a ring. I say that S is contained in some of the left ideals of R. Is this statement true or false? Somebody, is the statement true or false?
Sir, S is contained in R, but are you trying to say some proper ideas?
No, no, I am just saying some ideal.
Sir, S is contained in R.
Exactly. So this is true because R is an ideal of R. So S is a non-empty subset of R. So it should be subset. Okay. Yeah. So we must say that S must be contained in some left ideals of R. That means S is contained in R and R is an ideal of R. So this is true. So some of the ideals, so there may be many other ideals in which S is contained in. Now, as we know, intersection of ideals is again an ideal. I think you have already have this idea that intersection of any two ideals is again an ideal. So uh, let us consider the intersection of all the ideals of R that contain S. That means if I have this image like this, you have R, S is a non-empty subset, and we found that there may be many ideals which contains S, right? Which contains S. Now take the intersection of all the ideals of R that contains S. As the intersection of as the intersection of all the ideals of R containing S is again an ideal of R we can say that that ideal is the smallest or the biggest, is the
Smallest.
is the smallest ideal, is the smallest ideal of R, is the smallest ideal of R containing S, and that ideal is denoted by S. Okay, this ideal is known as the ideal generated by S. Repeating once again. Okay, so what we have, we start with a non-empty set S. S is a non-empty subset of R. So R is a ring and S is a non-empty subset of R. Okay. So what I am going to define? I am going to define what is the meaning of this cell L. Okay. So S is a non-empty subset of R. I claim that S is contained in some left ideal of R. So if is it true or false? So you mentioned that this is true because suddenly S suddenly R is a left ideal of R, and S is a subset of R. So this is true. Now we consider all left ideals of R that contains S. So consider all left ideals of R containing S and take their intersection. As we know that the intersection of arbitrary collection of ideas is again an ideal, the collection of all the intersection of all left ideals of R containing S is again an ideal. So the intersection section of all left ideals of R containing S is again a left ideal of R containing S. This left ideal is denoted by this, and certainly it is the smallest left ideal containing S. Okay, so this ideal is known as this left ideal. This is known as the left ideal generated by S. Okay. So similar thing happens right ideal, for right ideal, and this for both sided ideal. Okay. Okay. So I think this definition is clear to all of you. Okay. So let us first try to guess what could be how it should look like. For example, let's start with Z. So Z plus dot is my ring R, and say S is my, say, two element set. For example, say 2 and 3. So this is a non-empty subset of Z. Now we are trying to find, so since this is a commutative ring, so left ideal, right ideal, all these conditions will coincide, and so it's sufficient to consider both sided ideal generated by S. So we are trying to find what would be the element should look like. Okay. Okay. So first of all, there are plenty of ideals which actually contains S. Can you give some of the examples which contains, say, S? So this is S which contains 2 and 3. Can you tell me few of the ideals which contains 2 and 3? So 2Z will certainly contain 2Z. Okay, 2Z will contain only 2, not 3. Again, 3Z will contain only 3 but not 2. Can you tell me some of the ideas which contain all, both 2 and 3? Anybody? So suddenly you can
NZ,
understand what?
NZ, N is multiple of 6.
Yes. So 6Z is one of such example. You are absolutely right. Then 12Z. So though 12 is more than 6, but 12Z is certainly within 6Z. Okay, then 18Z. So 18Z and 12Z might have some intersection. Okay, so and so on. Now, if you consider the intersection of all this, so what would be the intersection of all this?
Sir, hello.
Yes.
Sir, how can 6Z contain 2 and 3 individuals?
Okay. How 6Z will contain 2 and 3? Very good question. So the answer that was given by, I think, Nikita is not correct, right? That's what. Is 2 belongs to 6Z? Yes or not? True or false?
So
2
false.
does false. So 2 does not belongs to 6Z. So Nikita, you gave the answer 6Z, right? So it's basically for competitive exam, this kind of things actually leads to some wrong impression. So that's what I always, the examples that I give you is actually motivate you to give a wrong answer, and sometimes it happens. So ultimately what we'll see that when it is 2 and 3, it will certainly be equal to the whole Z, but the way that I tried to argue you, you actually try to mislead you, and you are within the trap. So you see that 2 and 3, though they looks like the multiplication should be the 6Z, it's not, because 2 is not within 6Z. So ultimately what we'll see that if it is 2 and 3 together on a set, it will ultimately lead you to the whole Z. That we are going to show you. That was my motivation. But the way that I was trying to argue is basically you actually went to some other direction and you fall into the trap. Okay, now again, Nikita, can you tell me the story once again? Can you give me an example of an ideal which contains both 2 and 3?
That Z.
Suddenly Z. Okay, any other ideal which contains both 2 and 3? Any other ideal that contains both 2 and 3? Yes, now you have to think a bit. Okay, okay, now let's comes to the story that we have already defined in my last class, that if R is a ring and I is an ideal, and by some means if you are able to prove that one R belongs to that ideal, then what will be your conclusion? Your conclusion will be I
I equal
must
to
be
R.
equal to R, right?
Mm.
So here, if some ideal, if some of the ideal of Z will contain both 2 and 3, then from the property of ideal, A minus B will also belongs to I, right? So 3 minus 2, that is 1, should also belongs to I, right? And if this is 1 is within I, then what would be your conclusion? Then your conclusion will be I must be equal to Z. So there exists no other ideal of Z which contains both 2 and 3 together. Okay, is the concept clear to all of you now? Any question or doubt? Okay, now tell me what will happen for this set if I consider S to be, say, 2 and 4, or not 2 and 4, maybe say 4 and 6. Now tell me what should be this value. So here the answer was
Set to
ideal
Z.
ideal generated by this was whole Z. Now what is this? Okay, somebody tried to give me some answer. What was that?
To Z.
Okay, somebody told me 2Z. So is, do you really agree with, all of you, do you really agree with that? Okay, somebody, let's see who. Okay, Okopobo was there. Okay, Bonosri. Bonosri, what would be your answer?
Yes, sir.
Yes.
I
So
think
you
it's true.
yes. Okay. So you gave the 2Z. Okay. Can you tell me why this is true? Okay. Try to think intuitively. Then it will be easier for you to understand. So what I want some set which contains both 4 and 6. So as a result, it must contain 2, right? If it contains 2, it should also contain 4, it should also contain 6, it should also contain 8, and so on. So if it contains 2, then all the multiples of 2 must also be there. So multiples of 2 will also be there. So it should be 2Z intuitively. Now it might have, Z will also have the property which contains both all of them, but any ideal which is a subset of 2Z will not have this property because they are going to miss 2 then. If you consider any proper subset of 2Z, then that will certainly miss 2. So then the intersection of all these ideas intuitively, not a very formal proof of that, but intuitively, sometimes it happens for some exams when you have to give the only the choices. It's, you may not know the exact theory or the exact theorem, but sometimes for your own argument you can do many things. So it's a kind of hand weaving which is not very formal, but it gives you an idea. Okay, any ideal which contains 2, any proper ideal of 2z, which will certainly miss 2. Like it's the ideals will look like 4z, 8z, and so on, but that will certainly miss 2. So you have to be 2z must be here, and z will also be here, and any ideals which is not a multiple of say 3z, 4z will not be sufficient here. So then you have intuitively these two ideas, and the intersection should be 2z. So this would be one of the basic intuitive idea behind it. Okay, now we are going to formalize it. So now we have the definition of this, say both sided ideal or ideal or left sided ideal. Now we are trying to actually find what could be the form of S. So this is a kind of abstract way of writing things. Now I need some set theoretic description of this. Okay, suppose I know that this S is some say finite set, or maybe consist of say k many elements or n many elements. Okay, then we called this ideal generated by finite many elements. That means we call them this is finitely generated. Finitely generated. That means if the cardinality of S is finite, we call the ideal is called this finitely generated ideal. Okay. Now let us try to find some of the forms of this S. So, and that will be basically a kind of from very intuition we are going for that. So let us first have some idea. Okay. So S, let S be a non-empty subset of R. So S is non-empty. So what we want to check how this should look like. Okay. So let us try to. Now it's not Z. So understand, try to remember this is not Z. We have not mentioned whether R is a commutative ring or not. We have not mentioned whether R contains identity element or not. So R is any arbitrary ring and S is any non-empty subset of R. So for the time being, let S consist of two elements, say A and B. Okay, that will help us in constructing the intuitive logic behind it. Okay, now our aim is to find the smallest ideal which contains both A and B. Okay, so suddenly A and B must be within, say if it's we are considering only left ideal, so A and B must be within our L, right? And since this is an ideal, so this is R, this is my S, and this is the ideal generated by S. Since this is an ideal from the property of left ideal, so this is a left ideal from the take any R, so R A should also be within this, right? Similarly, take any element S, so SB will also be within this. And since they are ideals, their sum RA plus SB will also be within this. Now, can anybody tell me what would be the form of this ABL? Now, I give you enough hints, but still there is one point left. Let me check whether that missing point is being addressed by some of you. Is the question clear? I have taken an arbitrary ring. I don't know whether this is a commutative ring or not. I don't know whether the ring has the identity element or not. So I have just an arbitrary ring and I have S. For the time being, let us assume that S has only two elements, A and B. Now what could be the form of? So you know this definition. You know this definition is this should be the smallest left ideal of R containing both the elements A and B. Now I want to mention, I have given you few of the points that we should take care about then I want to ask you what should be the form of A, B, this L. Can anybody be, can anybody help me? So what should be the form? Anybody? Anybody? Just think about how it happens with Z. So giving you an hint how it happens with Z. Okay, try. I mean, it may be wrong. It doesn't matter, but you should speak and you should come up with something that you think. Whatever is there, try to express. Anybody?
So the ideal must contain Na plus say MB, and then all types of products between A and B.
Okay, tell me. Try to give me some of the idea. What should be like? Tell me
We
what should
can
I write?
take in A
Na,
plus MB,
NB, same N,
M.
MB.
So
Okay, MB.
uh, are we taking commutative ring?
No, no, I don't know whether that's a commutative ring or not.
We can take all types of products between A and B,
Like,
sums.
like.
We can take AB, we can take say A square B, we can take ABA.
Okay, then how to write it down in a formal way? So this N and M belongs to where?
So the integers.
Okay, and then so maybe this says that NM belongs to Z, RS belongs to R. Is it right? So
Yes,
you
sir.
don't you
Yes,
don't
sir.
need to then consider A square, AQ, and so on. Okay, so what Aniket told, I am writing it in that way. Okay, so since S is set with A and B, so what you understand that if A is there, then 2A must be there, 3A must be there, and so on. Similarly, if B is there, 2B must be there, 3B must be there, and so on. Also, as I mentioned, if you take any element from R, then RA should also be here, and say take any element S from here, SB should also be here, and RA plus SB will also be here. Like, so all these properties you need to take care. Now see, this is an element of R and this is an element of Z. If I add 2 times the element B, then I will have 2B. But this element is something different. So this is from the ring itself and this is from the ring. So these are and this thing are not same. That's why it should look like, so this in a form, like some integer A form and then some integer B form and their summation. Not only that, you should also include this like RA and also include SB and their sum, such that N and S belongs to Z, R and S belongs to R. So that will include all the say A and A square. See, A and A square is there. Why? Because you can consider A square as A dot A, and this A comes from this R. So you can have also 3A squared plus say 3A squared plus say 4B B cube. How can I explain this? How these elements are there? So first you can think, so A is here, A is here, 3A is also here because 3A is also here, and you can make 3A to be an element of say 4B as well. So you can make it this. So 3A square is also here. Similarly, 4B cube will also be here, and then their addition will also be here. So you can understand why these things are like this. Okay. Is it clear to all of you? Any question or doubts? Please don't hesitate to ask me. Is it clear to all of you? The form of this, is it clear? Okay. If that is done, then try to find arbitrary S. Now my S is a non-empty subset of R. Then how this S should look like? Tell me how this S should look like. So that should be some RISI, say I equal to 1 to n plus NISI summation, say I equal to 1 to k. If you want, do not like I, you can put it j. Okay, such that Ri belongs to R, I equal to 1 to n. Note that this n should also vary. You cannot make it fixed. This n belongs to natural number. Similarly, this nj belongs to z. Z equal to 1 to k. And this k should also vary. This is very important. Unless you put this n to vary, it will be fixed. It will always go to till n. But the idea is you might have sometimes R1 S1 plus R2 S2. You might have sometimes, you may put it like you can put it S dash here also. You may put it like say S dash. It's better to put S dash. You may be confused with S1 and also here S1, but this S1 and this one should be different. Like SI Sj dashed belongs to S. Okay, so that's the whole description. It may happen that they are here. It may happen that R1 S R1 S1 plus R2 S2 plus R3 S3, that is also there. Now if you make n to be fixed, then it suppose n is equal to 2, then only this element will be there. But how can you justify this element? That's why we need to vary this n. That's why this n is also varying here. That is very important. So you should understand this. Here also you cannot keep k fixed. That's why this k is varying here. So it's moving. And here we have S and S dash, that is from S. Is it clear to all of you? Any queries or doubt you have? Please let me know. So is it clear? Okay. Now let us come to the main result here, this proof. So this, you can say that this is a theorem. It says that let S be a non-empty subset of a ring R, then SL equal to what I wrote in the above. Summation, say I equal to 1 to n, say some element Ri, Si plus the addition, say j equal to 1 to k, nj, sj dash, such that Ri belongs to R, Si, Sj belongs to S, Nj belongs to Z, I equal to 1 to N, J equal to 1 to K, and both N and K, they belongs to natural number. Unless you give this one is very important. Unless you give this one, so this belongs to N means both N and K, they are also varying. Sometimes it's up to 2, sometimes N is 3, sometimes N is 4, and so on. So this is the collection. So to prove this, so I need to prove this. So it's just a statement. I need to prove this. So what is the condition that you know? We only know this definition. So what is that definition? The definition is, this is the smallest left ideal or the intersection of all left ideals of R containing S. So that is only the definition. And we have some expression here. We need to prove that both this expression, they match. So what we do, we assume that the right hand side equal to, say, L. Let the right hand side of the above expression be denoted by, say, L. That means this one. I write it like L. So this is my L. So to show this equal to L. Okay. Now just try to consider the definition here. So what is this? This is the smallest left ideal containing S. So if we can show that, so that is to show L is few things. First, L is a left ideal of R. Second thing we are going to show, L is the smallest ideal, or we can show that step by step. S is a subset of L, and third one will show that L is the smallest ideal of R containing S. Then what will be your conclusion? S must be equal to this one. Sorry, L must be equal to your this one, because it satisfies all the properties of this. Now, how to show that L is the smallest ideal containing S? What we need to show? That is to show if I, so this is smallest left ideal. Yeah. So if I is any left ideal of R containing S, then what I need to show? Then fill in the blanks. Can anybody tell me what would be the fill in the blanks here? To show L is the smallest left ideal of R containing S. So what we need to show, if I is any left ideal of R containing S, then I dash L. What should I write? What should I write to show that this is the smallest?
Sir, I
Somebody?
contains L.
I contains L. If I prove this, then we are done basically. Then I can, because I is an arbitrary ideal which contains S, and if I show that I always contains L, then basically L is the smallest ideal, because if we take any ideal containing S, then I can show that that ideal should be greater than L. As a result, L is considered to be the smallest ideal containing S. So that's the basic idea, or that's the formal way of writing. So the first thing that we are going to show that L is a left ideal of R. So it looks like a little bit like, the expression looks like a caterpillar expression, I say. So you need to show that first, that L is a, so this right hand side is a non-empty subset of R. Now tell me how to prove that L is a non-empty subset of R. Somebody? How to prove that L is a non-empty subset of R? So first thing, we are going to show that L is non-empty subset of R. How? Tell me. You, I am just showing you the expression for L. Now from this expression, tell me how I can claim that L is a non-empty subset of R. So what you need to show, you find some element which you can write in this form. If I can write in this form, then we are basically done. So tell me something, some element which is of this form, so that we can say that this is non-empty.
Sir, any element of the set is.
Sorry, could you please
Any
repeat once
element of
again?
the set. Any element of the set is.
Okay, let S belongs to S. Then yes, very good. First step is done. Then so you need to write S in terms of this. How can you write this
I
in
mean,
terms of
I
this?
should take A equals to 1 for the coefficient of S, and then rest of them are 0.
Okay, what you are telling, that 1 into S plus 0 into S dash. So you don't know whether S is there, so you can write it like this, right? But how can you assume that this is there within R? May not be, right? You have no idea whether, so it should come from R. So as per this notation matches, so as you mentioned, this is 1 into S. 1 means ring of R, identity element of R. According to this notation, it should come first, and then 0 into S. Yes, that is true. That is equal to R, S, sorry, that is equal to S, provided 1R belongs to R. But you have no idea, no clue, because R is any arbitrary ring. It may happen that R does not contain the identity element of R. Then how to justify? Is it clear? Okay,
Yes, sir.
but it was a good try. Yes, tell me any others. So how to write this S in terms of this, so that all these conditions are satisfied? I can say you that your expression is almost correct. Try to
Sir,
figure out.
what
Yes,
if I take 1 from Z and 0 from
one from,
the element? 1 from Z.
yes. So if you just make it a reverse, like uh, it should come from 0 element of R into S plus integer 1 into S, right? So this is the integer, this belongs to Z, it is always there. because nj must be from z and s dash from s, so it should be dash. So this part is done, and this r should come from the ring, and I am putting it as 0r, that is the zero element of r into s, so that becomes 0, that is zero element of r plus this is nothing but s, so ultimately this is s, and that belongs to l, no doubt about that. Is it clear? Is it clear to all of you? Any question, any doubt? Please let me know. Anybody have any, anybody has any query or question? Okay, so this element belongs to s, that's why that implies l is non-empty subset of r. Okay, so the first part is done. Then we need to show that this is a left ideal. So this element, that is very easy to prove. Next we show that l, so the part is okay. If I write it roman 1, then I should write it roman 2. L is a left ideal of R. How to prove that? Non-empty part we have already proved. So we take two elements. So how does it look like? It should look like summation, say Ri Si I equal to 1 to say n, plus summation Ni say Si dash. So Nj maybe j equal to say 1 to m. So this is one element, and say another element we can take I equal to 1 to say n bar r I bar s I bar plus summation j equal to say 1 to m bar n j bar s j bar dash. So really it looks like a caterpillar expression. So let these two elements belongs to L. Then you can check that if you take a minus b, so if I consider this to be element a and this to be b, then suddenly you can check that a minus b belongs to L, no doubt about that, because the with respect to this addition this is commutative, so you can bring this element and this element side by side, and then this element and this element side by side after a minus b. Okay, so these two elements will be paired because plus is commutative, so you can do that. So a minus b will certainly belongs to L. Then to show the left idealness, what we need to check, take any element r from R, then just r into a, that means summation of r, you can understand that this will get in and that will also be get in, and as a result that will also belongs to L. So what will be your conclusion? That your conclusion will be L is a left ideal, left ideal of R. So the first thing that we have claimed here is already done, that L is a left ideal of R. The next thing that we need to show that S is a subset of L. Can anybody tell me from the structure of L, how can you prove that S belongs to L? How can you tell that S belongs to L? If you look at this
Sir,
argument that we have already done, from there it's clear that L is a S belongs to L, because we started with an element S and then finally we showed it that S belongs to L. So what would be your conclusion? S is already within L. That is also proved through this step, right? Orkoprobo was trying to say something. Yes, Orkoprobo.
no,
Any
sir, I
question?
was just trying to say, I was just trying to say exactly that
Okay,
we
yeah,
started with it.
yes. So this is also done by using this argument, the same argument. So as S is a subset of L and S is a non-empty subset of R, so L is certainly be non-empty. So by using this argument at the very first step, we could have done this. Okay. So the only thing that is left with is L is the smallest ideal of R containing S. So that we need to show. That means we will take any ideal I which is a left ideal which contains S, then we will show that I must be greater than equal to L. Then we are basically done. So let's start with that. So what we are going to do, we take any ideal. So let I be any ideal, any left ideal. So here we are dealing with left ideal. So left ideal of R containing S to show I. So what to show? That is, take any element from L and then try to show that that belongs to I. That's all. So let any element, how it looks like? It looks like I equal to 1 to say M Ri Si plus summation j equal to 1 to M say Ni Si is sorry Nj Sj dashed belongs to L. How to show that that belongs to I? How will you prove that that belongs to I? See, this part S dash belongs to S and S dash is also within I. So this part is very much within I. Similarly, this part is also very much within I because I is a left ideal and S belongs to I. As a result, Si into so Ri into Si, that will be within I from the property of left ideal, and their summation will also be within I. So as S is a subset of I, this element, if I consider it to be A belongs to I. That implies L is a subset of I. What we need to prove. So we are done. So as a result, what we say that this now all the properties of this, so this is the smallest left ideal containing S is nothing but L. So now we have the form of S, right? Is the proof clear to all of you? Is the proof clear to all of you? Any question or comments? Okay, fine. Now I am going to ask you the question. So in my last theorem, what we have assumed that R is any arbitrary ring, right? Now I assume that R is a ring with 1. So my theorem statement is let R be a ring with identity element and S a non-empty subset of R. Then SL should look like what? Okay, now tell me, who should tell me? Uh, who is there? Oh, Shri already done. Bhaskar. Okay, Bhaskar, can you tell me what should be the form of this? Remember in my earlier one, the form looks like this, right? Now tell me what should be the form of this if the ring is with 1. Bhaskar, are you there? Bhaskar?
Yes, sir.
Okay, tell me. So you can understand that, of course, this should look like something similar to this, but you have some extra privilege that you have already with you the identity element. Then what extra that you can benefit, or can you make it little shorter? Giving you an hints, some of the terms will not be present here if the ring is with identity. Okay, try to guess why I am taking this one. Any idea why I have taken this expression? Because if some s j dash is there, this plus is j dash should also be there. Okay, that means it is 2s j dash, and this 2 is nothing but an integer. So you cannot cover this integer by this r, because r is an element from the ring. If it is within z, then it is fine, but since it is not within your ring, this 2, you have some problem. That's why we had to take this one. Now you have some extra element that you know that the identity element is within this. Then what would be your form? Any idea? Okay, let's see. Krishnendu, Krishnendu, are you there? Krishnendu,
Yes,
are you
sir.
there?
Yes, sir.
Yes. Can you please tell me what you should have some simplified form, and I'm telling you this should be your point of interest. Can you remove these terms? So you know now this identity element is with you. So can you have by some chance 2 can be now removed? Okay, Masud, are you there?
Sir, I'm thinking.
Okay. Safik, Safik, are you there? Okay, Nikita, are you there?
Yes, sir.
Yes, can you please try to explain?
Hello, sir.
Yes.
Sir, if we proceed with your example like sj dot plus sj dot equal to 2 sj dot, then
Yes.
we can write down 2 as 2 dot 1, and this 2 dot 1 will belong to R because R is a ring with
Yes.
unit.
So, yes, very good. So you can write it like this, right?
Yes,
So you can write this. So this is your 2IR dash. That means this part you don't require. Okay. As a result, you can write like summation I equal to 1 to n Ri Si. And this part you can take care with the help of this Ri and 1 R. Such that, as usual, Ri belongs to R, Si belongs to S, I equal to 1 to n, and n varies. Okay, quite simplified. So now you can understand a ring with one and without one has a lot of difference. So it gives you a kind of extra advantages because it gives you uh, quite simpler form of this R. Okay, now tell me somebody, we are considering, you can understand the same thing will happen for right ideal as well. Now if I have only ideal, I mean it should be, so S is a non-empty subset of R, and this both-sided ideal, how it should look like. I have no clue whether this is commutative or not. I have no clue whether this is with one or not. How it should look like. Somebody, Aniket, can you tell me how it should look like?
So in this case, we can take a summation RISI.
RISI.
Uh,
Then
uh, such that SIs come from the capital
no,
S.
no, no. It's not yet. It's a it. I don't have no idea whether it has with one or not. It's an arbitrary ring.
Okay, sir. Okay, sir. Then we have to add the NISI terms. The summation NISI.
Okay, and that's all.
And yes, sir.
I am talking about both sided ideals.
Okay,
Yeah,
sir.
it
Okay, sir.
means
Understood.
are in with unity.
No, not no idea, because this is an arbitrary ring.
Then we need one more term. We need a summation SIRI.
So S, say this is okay. I should write it J. Maybe I should write it
Okay.
SK RK. Maybe RK dash, and maybe double dash. I put it there. That's all.
Yes, sir. It seems like it.
Okay. Suppose you have R, any element of R, and you have an element of S. So this should be here, and you should have also S dot R should also be here. Now, what will happen? Say T T dot S dot R. So T and S, they from R. How to address this element from here? How to address this element, this kind of element? S is from S, and whose left side and right side elements are multiplied with R, and maybe their summation something. How will we address this?
Okay, sir. Then we can take a different type of expression. We can take summation NISI and then summation RISI RI prime.
RISI RI prime.
Prime.
But then how will you express this from here? Will
Oh,
it
then
be will
we don't
it
have
give
the
you
identity.
identity element? You no idea whether it will have identity element or not.
Okay, sir. Understood. Then we can add this type of term in the expression that we have written it above.
Yes. So maybe RL, say triple prime, S L triple prime, and maybe T L triple prime. So now it's complete. Okay. So now if you have two of this, how will you express this one? Say this element, summation of this two. How will you express this then? Is the question clear to you? How will you express two of this by using this? Which term will represent two of this by this? So two of this is will be represented by this itself, because you can just write it this plus TSR. That's all. That will be basically two of this. That will be taken care by this. Is it clear? So that's all. So that will take care all. So now you can understand what are this S dash, S triple dash, and from where to where it should vary, and that should also, this upper index should also vary. So you'll be maybe it really looks like caterpillar, and to prove that that is the smallest ideal containing S, the idea is very easy, but to write it, it may not be that easy. It will be very messy, nothing else. Okay, so that's the expression for the ideal generated by S. Now tell me somebody, if S consists of only one element, say only one element, say A, in an arbitrary ring, in R arbitrary ring, how it should look like? What should be A L? How it should look like? Now it should be clear to all of you. Tell me, what should be? What should be the expression for left ideal generated by A?
The summation RIA
Summation RIA
plus summation NIA.
plus summation NIA.
NIA.
Good. But you can again have some, might have some simplification of this. So RIA, if I for I equal to 1 to 3, you can write it like this: R1A plus R2A plus R3A. So you can use the distributive property, and whole thing you can replace it by R. That means it should represented by RA, right? So you can think this as RA, and similar way you can consider it this as NA. So the story here should goes like this: if this is only one element, then it should be like RA plus NA, such that R belongs to R, N belongs to Z. That's all. Clear? Now tell me what will happen for, okay, so this kind of expression, if I want to write with one, say I consider this in a ring with one R, then what should be the expression? Somebody tell me what should be the expression. If you understood the whole class, then you must be able to tell me what would be the expression then.
RA such that R belongs to capital R.
Very good. Because NA term will then vanish like my previous cases. So these ideals are called principal ideals. That means the ideal generated by by a single element. Okay, so if S sorry, if S is finite, if S is finite, then we call S as finitely generated ideal, as finitely generated ideal. Okay, so that is the basic definitions. So this principal ideal plays an important role in ring theory. Okay, later on we'll learn what is the definition of principal ideal domain and all. So you can understand that in Z, whatever may be, you can consider whatever may be the set, say 4 and 40. Then what is S? Quickly, can you quickly tell me what is S? What is S? If S is 40 in Z, then what is ideal generated by S? Quickly. Now it should be very easy for you to tell me.
Suppose it.
4Z. So you that means the ideal generated by 4, right? So because just now we have seen that it should be, if the ring is with 1, then it should look like RA, where R comes from A, sorry, R. So here this A is 4 and this R comes from Z. As a result, it looks like 4Z. The idea here is you can see that in Z, any ideal should be generated by a single element. Can you tell me Z is an ideal of Z? Z is generated by which element? So as I mentioned, yes, we'll prove it later on, but it is a special property that Z has. It's the 1. So Z is generated by 1, because as you just seen that it should be like 1 R into 1, so that R comes from Z. So it's nothing but the Z, that means R belongs to Z, and this is nothing but the whole Z. So now it's very clear to all of you, I guess. So all the elements, all the ideas of Z are basically generated by a single element. If an integral domain, we all know that Z is an integral domain. If an integral domain has this property, we call that integral domain as principal ideal domain. Principal ideal domain. Domain means integral domain. So an integral domain, an integral domain in which every ideal is generated by a single element of the ring. So as you understand, any ideal of basically Z looks like NZ, and you can understand NZ is nothing but N, ideal generated by N. So any ideal is basically generated by a single element. As a result, Z is a principal ideal domain. So we will talk about principal ideal domain in details in maybe after 2 or 3 classes. But for the time being, when you understand that the ideal generated by a single element, ideal generated by finite number of elements, or ideal generated by any non-empty subset, maybe in a ring with 1, maybe in a commutative ring, maybe without identity, and so on. So now you have the idea that how it should look like. And it from a book, if you read this expression from a book, if you read this expression, you will suddenly find that, okay, how it looks like. Either you just try to remember all the things, mug it up, or you have to justify. So it comes very naturally. So try to think in a deeper way, then you will able to understand that that is the only possibilities that one could have. Though it looks like very messy, but it has lots of justification why it should be like this. So that's the way that we should learn things. Otherwise sometimes it may be difficult for you. You have to just remember, but you cannot remember everything. So unless you have some basic intuition, basic idea, you won't be able to completely do all those things. So it requires your basic intuition. So the main aim of this class is just to highlight you few things that you should not mug it up, but you should justify yourself so that the expression will come automatically. Okay. Now we come to the my original problem. What was, so it was a polynomial ring, and then I need to prove that this is isomorphic to Z. So that is my whole idea. And now it's quite clear to you that what is the ideal generated by X. So we are now in a polynomial ring ZX. So the elements of the polynomial rings looks like a polynomial, say A0 plus A1x plus an x to the power n. So this is my one polynomial fx looks like. So that is within zx. Okay. Now can you please tell me from the definition of this in this ring, what is this definition? Ideal generated by X. Just now we have just seen that it should be like R into X, from where R should come from ZX. That means it should be like a polynomial into X, such that this polynomial should come from ZX. Okay. Now it's always multiplied with X. Now can you tell me what is the special property of this? If you consider fx like this, what is the effect of this by multiplying by x? Can somebody be tell me what is the extra property over this? So just in terms of the coefficients. So what is
That the
the, yes, yes, I get your answer.
constant time will be zero.
Yes. So here you can see that if you multiply it with any polynomial with x, then in this multiplied term you cannot have the constant term except 0. So 0 you will always get the constant term as 0, because if you multiply this then it will be a0x plus a1x square and so on. As a result you won't get any constant term which is non-zero, so you will get the constant term as a zero element of the ring, that means Z. That is very important observation. Now we want to prove this. So as I mentioned, it looks like the form looks like the first isomorphism theorem. So we might we may make a function from here to here. F is a function from here to here. So we need to define a mapping so that that would be a homomorphism, and if it would be an epimorphism, then we can directly use this result of first isomorphism theorem. So let me first define a polynomial. Say let px equal to a0 plus a1x plus an x to the power n. So be a polynomial in zx. Now the question is how to define this. So you can understand that all these terms are from z. Now you need to prove that Karef should be this. Okay, that's what your aim. You want to prove that ideal generated by X should be the kernel of F. Then only you will be able to prove this result by first isomorphism theorem of ring theory. Now the point is, how will you prove that this Karef is equal to 1? Anybody?
So we
Well,
will
how?
define the function to the constant
Okay.
A0.
So he is telling, he is defined this. So first of all, let us check whether this is a ring homomorphism. It's very easy to check. Then F is a ring homomorphism. Ring, you can say directly epimorphism, because you can take any integer here, then you can always construct a function whose constant term is that integer. Then that will be an epimorphism. Is a ring epimorphism. Okay. Then by first isomorphism theorem, you will have ZX quotient kernel of F will be isomorphic to image, and since this is an epimorphism, image must be equal to Z, so that is Z. So we are almost done. So what we need to show, we need to show we need to show Z, we need to show car equal to kernel of F equal to ideal generated by X. So let us try to find what is kernel of F. This is nothing but all such polynomial fx belongs to Zx such that, so maybe we can write not fx, maybe px, all such polynomial px belongs to Zx such that f of px equal to the zero element of z, and that is nothing but z. So all such px such that f of this means the constant term. So the constant term a0 should be equal to 0, and that is nothing but all the polynomials of the form. So all such px, you can write it all such px of this form. I am just making it one step ahead. So this is all such polynomial a0 plus a1x a n x to the power n belongs to Zx such that f of this means a0 equal to 0. As a result, you will get all the polynomials of this form a1, so I am just writing it here, all the polynomials of this form a1x plus a2x square plus an x to the power n belongs to z zx, sorry, zx. And this is nothing but you can take x common, and that is nothing but the ideal generated by x. So you prove that this is nothing but your carf, and by if you substitute this here in your first isomorphism theorem here, you will get the answer. So now you can understand that zx is basically zx quotient x is isomorphic to this. Is it clear to all of you? Is there any question or comments, doubt? Please let me know. Okay. So from here, I just give you few things that you need to read from the book. The things are here. I'm mentioning it. Few operations. You can read any of the books. So Damit Foot or my book or Malikshan Moderation. This is if I and J are two ideals of R, then what is about this operation? What is I plus J and I dot J? So you need to define these two operations plus and dot over the ideals so that both of them, they will also become ideals. So ideals of R. So that part I think it's not very difficult. You can study from any of the books, then you will able to understand what does it mean. So maybe from the, I mean in the next class, I'll go for prime ideals, maximal ideals and all. But before that, I may do a little bit on it. Okay. So till now, any question or comments if you have, please ask me.